So last week then we were looking at finding the equation of a line from a set of data, and I just want to quickly review those things we set up, those points to plot it. So first of all, we plot the data on a set of axes, make sure it's a useful scale. We put the independent variable on the x-axis and the dependent variable on the y-axis. The one we're controlling goes on the x-axis generally, so that's often time, because we can control the time. We'd take a measurement every 10 seconds or every minute, something like that. Or temperature, we could control the temperature and note something every 10 degrees or something. So we identify those axes, set up our scale, put the data points on, and then draw a line of best fit. And we talked last week about what to do if there's a rogue bit of data. We might well ignore it, but if we get the opportunity to go back and have another look at the raw data and see if there's an error made at that point. We talked about the idea that if the data suggests a straight line, of course it might not be like this, everything exactly on a straight line. So then you've got the problem, you know, where is the line of best fit going to go? And does this data actually suggest a straight line? So that's all something that you have to just sort of judge as you're doing any particular one. We talked about something that we're going to do a little bit more on today, which is what do you do if it's not a straight line, it suggests some sort of relationship like this? Well, the answer is we try and recognize what sort of curve that suggests and then turn the data into something we can put onto a straight line graph. I'll look a bit more on that today. So once we've got our straight line, there's two things we're after. One is the y-intercept, which might go through the origin. So in that case it's 0. But if it's not going to go through the origin, we've got a little bit of a problem when especially if we're drawing it by hand on a graph paper, because we don't know before we draw it where the y-intercept is going to be. So we need to set the y-scale so that we allow for the fact that the y-intercept could be quite a long way off our scale, above or below. So that can be a problem. You might draw out your data and find that actually it doesn't cut the y-axis. So we find the y-intercept, and then we find the gradient. We talked about how we do that. Divide how far you go up, how far you go along, y divided by x to get the gradient. And then you write down the equation of the line. There it is, y equals mx plus c. M represents the gradient and c the y-intercept. And so for our example, if I was plotting volume on the y-axis and temperature on the x-axis, my equation of this line would be v, so y would be replaced by v because that's what I'm plotting, equals 0.4, which was the gradient, times the temperature plus 20, which was the y-intercept. So that's the plan. And then we had a look at an example, and this is the one I asked you to do. This is something that often happens. If you've got a set of data where you've got some really, really small values, or it could be very large values, and you want to try and put that on an axis, you don't really want your scale to be going 0, 0.00001, 0.00002, and so on. It all gets very unwieldy. So we use the fact that we can actually shift the decimal point using engineering notation, and so I could call 0.407 70 times 10 to the minus 6. So 0.3039 would be 390 times 10 to the minus 6. So long as I make sure this is the same every time, times 10 to the minus 6, then I can put that on my data. I can say the strain is going to be times 10 to the minus 6. So then I put 70, 130, and so on in. Gives me more reasonable data to put on the graph. And then I asked you to plot the graph and get the equation of the line. What I've done is I've put these data points onto autographs. So I put the data into here, look. X-axis 4.9, y was 70. Is that the right way around? Let me just check before we go any further. X was 4.9, y was 70. Yeah, that's right. So I've got it the right way around. This software allows you to swap the scales if you want to. Look, if I put them the wrong way around, it could have actually hit swap axes and then it would have swapped them over. To enter this data set, I hit this button, which is the enter the data button. If you don't remember that's the right button, then up here, look, it says data, so if you hit on that, you'll get the option to enter a data set. You put your number in, hit return, and it jumps to the next place. 70, hit return, jumps to there. 8.7, hit return, and so on. When you put your data set in, hit OK, and often actually you find that, if I were to zoom out, sorry, zoom in, initially you see absolutely nothing, and that's because the default scales are set so that you can't see your data points. So zoom out, which is this button here, until you start to see the data appear. And there it is. What I need to do now is to zoom in on the y-axis. If I zoom in on the y-axis, that will stretch these data points out. So zoom in on the y-axis is this button here. And click, and you see the data points start to move outwards. This hand tool is quite handy because it moves the axes around where I want them. So I can look at this now and try and find the equation for line. So to do that, I put data, enter an equation, and type in y equals mx plus c. Hit return or hit OK. I get my line. And now, this is what I want you to do with an example that I'm going to give you in a minute, or we can check the one that you've done already. I will now just adjust, using this constant controller, the values of m and c until I get a line that goes through those data points. I suggest you adjust m first to get the line parallel with the data points. Actually, it's not going to be far off through them, is it? So it looks like my y-intercept is round about 0. Is that what you found? Okay. So for this particular set of data, the y-intercept is 0. And looks like m is round about 14.2. So if you plotted yours on the graph, you should have got a gradient of around about 14. However, of course, what we've plotted on here, this isn't correct for the gradient, isn't it? Because what we've plotted on here, remember, is on this axis goes x, and x is the, let's remind myself, which is x. X was the, okay. Oh, okay. X was the stress. So up the y-axis is the times 10 to the minus 6. So going back to my autograph, the y-axis is really times 10 to the minus 6. So let's just reduce this down a bit. Close this. Get rid of that. So okay, what's it doing? It's allowing me to do this a minute ago. Oh, yeah, that's right. No, it's not letting me doing it now. Okay, never mind. So I've got to remember that the y-axis is times 10 to the minus 6. So to get the gradient, it's whatever this gradient is measuring times 10 to the minus 6 divided by the x. So actually my gradient is going to be whatever it says on this constant controller, 14.2 times 10 to the minus 6. So that will be your final gradient. Don't forget that at the end, when you put your values in to find a gradient, you've got to remember what you've done on the data points, which was to call each of these data points on the y-axis times 10 to the minus 6. So you must take that into account when you work out the gradient. Does that make sense? So let me put this autograph solution on in the notes for you. So you've got it there. If I put this up here. And then capture the screen, keeping the value of the gradient in there. Then I can put that into the notes for you. Okay? So that's a graph of the solution for this question here. So what I'd like you to do, if I give you sort of 5 or 10 minutes now, is just to log on, start up autograph. You find up there on the start menu, and then put your data points in and plot the graph, and try and get that, try and confirm the gradient that you got for this set of data. Right, let's have a look at this then. What I've put into the notes now is another set of data from the textbook that I want to plot on autograph. This particular question is plotting the value of the load in newtons and the distance obtained experimentally. So we put a load on and we measure the distance the thing travels. Let's have a look at what this set of data looks like on autograph. There, I've put the data points in, so exactly like you would have done. Hit OK. Can't see any data points, so let's zoom out. Here are some data points starting to appear. So again, I'm going to need to zoom in on this x-axis to get the data points to spread out. And now I see I'm certainly not getting a straight line. I'm getting a curve. So the question is, what sort of curve is this? It looks like, actually, what I've probably done, if I look at this, because this is not quite what I was expecting, have I put these data points the wrong way around? I'm going to plot D on the x-axis. The distance 0.75 on the x-axis. Have I done that? I go to the data points here. Have I put D on the x-axis? D is 0.75. Yep, I have. Now, what have I done now? Right. So the data that we have certainly doesn't look like a straight line. And in fact, if we look at the question, which is outlined in the notes here, it says that the law is the suggestion that the law is of this form, that the load equals some constant A divided by D plus a constant B. And we've got to find the values of A and B. So what we need to do is plot a graph that will give us a straight line and then find the values of A and B. So what we do is we say to ourselves, okay, if the law, let's go back and extend this page, if the law is of the form load equals A, which is a constant, over D plus B, which is another constant, how are we going to relate that to the equation of a line? That's the idea. What we do is, first of all, algebraically, do you remember we've talked before about this idea that A divided by D, in this case, is the same as A times 1 over D. Dividing by something is the same as multiplying by 1 over it. So I can write this as load equals A times 1 over D plus B. Now, if we compare that with the equation of the line, y equals mx plus c, if I now plot load on the y-axis and 1 over D, and that's the key, on the x-axis, so I don't plot D on the x-axis, I work out what 1 over D is, and then if I plot y against x, or load against 1 over d, I should now get a straight line, and the gradient of that line will give me a, and the y-intercept will give me b. So if the relationship, and certainly in this case it doesn't look like a straight line, isn't a straight line, we can make it a straight line by guessing, and it's normally an educated guess, because in an engineering situation you normally know what sort of relationship you're looking for. And so we say we know that we're expecting it to be a 1 over d relationship. Then we plot not load against d, but load against 1 over d, and we should get a straight line. So if I go back to my data points here, or back to the question, I need to add another column, which is going to be 1 over d. So let's start a table of results off underneath, like we did last time, and then you can complete it and try it out. So I want load against and distance. Load I'm going to end up putting on the y-axis, because that's going to be my y variable. D is going to end up going on the x-axis. But I want to work out what 1 over d is. So if we go back to the original set of data, load of 32.3, distance of 0.75. What I need to do is work out what 1 over 0.75 is. 1 over 3/4 is the same as 4 over 3, which is 1 1/3, so it's about 1.33, something like that. Okay, so then what's the next piece of data? 0.37 and 29.6. Work out what 1 over 3.7 is and put that in. Anybody? 2.7. And so on. And now what I'm going to do is plot this set of data against this set of data. I'm going to put that on the y-axis and that on the x-axis, and I should get a straight line. So what I'd like you to do is to complete that table for the set of data. I'll put the data set in view so you can see it. If you've actually got the textbook here, you can find it. What page are we on, Richard? 270. So if you turn to page 270, you'll actually see this question outlined there with the table of results. But you can generate that yourself if you want, and then plot that on autograph, please, and you should get a straight line, and you can find the equation of the line. If we look at the data and we generate our table of load against 1 over d and plot that at autograph, we get that curve, load against d, and that suggests that load is proportional to 1 over d. So you sort of get to know these relationships. So instead of plotting load against d, we plot load against 1 over d, which you've just done, and you get a straight line. This time, of course, the gradient is negative. It's a diagonal, isn't it, Sam? Okay? And that gives us a gradient of -2 because it's sloping downwards from left to right. So we get our values for A and B, we can plug those in. A turns out to be about -2 and B about 35, something like that. Okay? Questions? No. You don't need to save it. So, what I would like to do now is hand out some practice questions for assignment 1. So these practice questions, which I've just handed out to you, I've put up on here. This is for assignment 1. So we've got about half an hour now to have a look at these, and just before the end of today's session I'm going to hand out the assignment, which is going to be very similar to these. So let's just have a look. What is the assignment going to be about? First of all, it's about the laws of indices and combining powers. If the base is the same, which is in this case, the base is always V, so same base. We don't know what that base is, but we know it's the same because it's the same letter. So I can combine the indices, knowing the laws of indices. So that's what question 1 is about. With varying complexity, you need to look back at those laws of indices and try those questions out. So there's a little bit of revision involved. And then we looked at the laws of logarithms to solve indicid equations. This question here is to do with solving indicid equations. So look back to those examples we did on those. Try that question. And then question 2 is about plotting a straight line graph. I've got some graph paper here. In the assignment, I need you to plot it by hand to demonstrate that you can draw a line of a graph and put on a line of best fit like we did last week. But what I'd also like you to do is confirm that by doing it on autograph and printing that out. So when you get to question 2, you can practice with this one, but the assignment question itself, I'll need you to do it on graph paper and on autograph. And then question 3 is about factorizing an algebraic expression, taking out what's common to the terms and putting them outside a bracket. So you can look back on what we were doing on those as well. So 3 questions to do with the pass part of assignment 1. There is a merit question to come, but if you look at it, this will allow you to achieve pass 1, 2, and 3. So about 20-25 minutes now, please, to have a go at those questions. Have a quick look then. So let's look at these practice questions. So the first one is to do with the laws of indices. If we look at them, the first one, the base is the same, and so what do I do with the powers? I add them because I'm multiplying them all together. So 4.5 plus negative 0.4 plus 0.75 plus negative 2. Just be aware of the signs as you go through that. So 4.5 minus that is 4, 4.75, so v to the 2.75 will be the correct answer for the first part. The second one, same sort of idea. D, so the base is the same in all of these. So negative 1.5 plus minus 0.5 is negative 2. Plus 0.4 is negative 1.6. So this gives me d to the negative 1.6 squared. And the law of indices that's involved here is if I've got one power and then it's all raised to another power, I multiply the powers. So this will give me d to the negative 3.2. Okay. The last one, what I need to do here in parts is to first of all divide the v squared by v cubed, and to do that I subtract the powers. So this gives me v to the minus 1, 2 minus 3 is minus 1, multiplied by v to the power, this one's a bit awkward, 1.2 minus, because I'm dividing, minus 0.5 becomes 1.2 plus 0.5, which is 1.7, multiplied by v to the power 4 minus 0.8 is 3.2, and then I add those powers together and finally times the answer by 3 to get the solution. Okay, so just taking it step by step. The next question, indicial equation to solve. I'm after x, which is in the power, so the first step is to take the log of both sides, which means the 2x plus 1 can come down and become a multiply, times the log of 7.5 equals the log of 135. And then divide both sides by log 7.5. I'll get 2x plus 1 equals log 135 over log 7.5. And then it's an equation to solve to find x. And x turns out to be, Richard? 0.717, thank you. So you should get that answer at the end, and you can always check you've done it right, because remember what you do is you put this value for x back into the original equation and check you get 135 as your answer. And you've got the notes on those, Ben, to hand out to Charlie. Okay. So that's that question. Question 2, well, we've gone over a lot of that today, so I'll leave you to look at that one. The last one, question 3, factorizing, is all about taking what's common to both outside the brackets. 3 is common to both, and so is x. To decide what I'm left with inside, I just multiply 3x, which is what I've taken outside. I ask myself the question, what have I got to times 3x by to get back to 3x? 1. What have I got to times 3x by to get back to 6xy? 2y. Check it's right. 3x times 1 gives me back 3x. 3x times 2y gives 6xy. I could partially factorize. 3 is common to both, so that would leave me x plus 2xy inside. That too is factorized. And I don't say in here that you need to fully factorize, which is what this one is. That's fully factorized. So that would be correct too. That's factorized. I could also just take the x outside to leave me 3 plus 6y inside. So any of those answers would do. The next one down, well, 2 goes into 4, 6 and 12, so I could take 2 outside. There's at least one x in each term, so I could take the 2x outside, leaving, what would the first term be? What have I got to times 2x by to get 12x squared? Any? 6x. Right. How do I check? 2x times 6x gets me back my 12x squared. Next term, what have I got to times 2x by to get minus 6x? Minus 3, yeah. And the last one, 4, so that's 2x squared. Check you've got it right. There's no reason that you should get this one wrong, because you just multiply it back out again, and if you get back to the original one, you know you've done it right. And that's all I'm going to do to check it. Multiply your answer back out and check it comes to the solution, to this question rather. Okay, I'll now hand out assignment 1 and we'll call it a day.